Hi, good afternoon. Um, let's see, we're going to retrace our steps a little bit and try to pick up the trail we were on last week. Remember, we're on chapter 3 of the textbook, about, I would say, halfway through or close to that. And hopefully today we can get most of the chapter, if not all of it, over with. So let's briefly review what we saw last Thursday. We went over the signal representation between baseband and or low pass and bandpass. Remember, we said that essentially we can superimpose two different signals. One signal that is transported by a cosine of a certain frequency, and another signal that is transported by a sine of the same frequency. And these two signals can coexist, one on top of each other, and be completely differentiated because they're orthogonal. So their low-pass equivalents are, for the cosine is a real signal, and for the sine is an imaginary signal. So we call these the in-phase and the quadrature signals. And as I said, we can superimpose these two signals, and even though they will seemingly mix up, we can actually completely discriminate one from another because they live in orthogonal dimensions. So essentially what this implies is that we have two different dimensions over which we can communicate, the in-phase and the quadrature dimensions. And any good communication signal is always going to be making use of both dimensions. So when we talk about digital modulations, we'll see how the best modulations are the ones that use both the in-phase and the quadrature dimensions. So we went over the conversion between signals in the passband domain and in the low-pass domain. Remember, we call S of t the passband signal and U of t the low-pass or baseband signal. And the conversion is to this operation. We take the real part of the low-pass signal times this complex exponential of the particular frequency, and that gives us the equivalent, the corresponding passband signal, and vice versa. We also described or defined the amplitude and the phase representations, which is an alternative representation to the in-phase and quadrature. And we use A to denote the amplitude, and we use phi to denote the phase. And then we went through a review of random processes. So hopefully by now you master all this topic of random processes, which we'll make very heavy use of today. So we cover a number of properties, especially, remind you, we talked about ergodicity. Remember, when things that happen in the time domain are equivalent to things that happen in the probability domain. So we'll be using these today. And then we started talking about small-scale fading, which has to do with features that manifest themselves over very short distances on the order of a wavelength. So typically for us, that would be on the order of a few centimeters. And to facilitate the study of this scale of fading, we typically regard all the other features we studied so far, which are path loss and shadow fading, as locally fixed. So we look at small distances over which the shadow fading and the path loss are pretty much constant, and the only thing that matters and changes very fast is the multipath fading. So this is a typical picture of a multipath scenario, transmitter and receiver, and a whole bunch of objects that are reflecting signals. So there's a number of components. Each one has certain amplitude and phase, and a Doppler shift that has to do with motion, and a delay that has to do with the length of the corresponding path. So this whole thing gives rise to a linear time-varying channel impulse response that relates the signal that we transmit and the signal that we receive. So essentially the received signal relative to the transmit signal is given, the relationship is given by the summation over, so each of the terms in the summation is one of these multipath components, one of these reflections. And each one has a certain amplitude, alpha, certain phase, phi. There's n of these components, which can also be a function of time. And each one has a delay, tau sub n. Okay? So these are the main quantities that are involved in this formulation. Same thing can be written in the low-pass domain. And in that domain, we can express actually the relationship between the signal transmitted and the signal received as a convolution with an impulse response. So this is the typical impulse response of a time-varying, linear time-varying system. Then we went over the Doppler spreads. So each of the components has a certain angle, theta sub n, for the nth component, relative to the vector of motion. And so the speed vector has a certain projection on this direction of arrival. And as a result, the frequency of the signal is changed. It's compressed or expanded, depending on whether we're moving away or into the signal. And that's what the Doppler characterizes. So this shifting frequency compounds over time into a changing phase. So the phase is now a function of time. It has a certain fixed phase that depends on where we started, plus a term that builds up over time that has to do with Doppler. And a signal that at origin, at transmission, has frequency f sub c is going to arrive with frequency f sub c plus f sub dn, where this is the Doppler shift of the nth component. And this Doppler shift, so the change in frequency, is given by this very simple formula. It's just the speed of motion divided by the speed of light times the frequency of the transmission times the cosine of the angle over which this particular multipath component is arriving, right? So this cosine times the speed is the projection of the speed, so it's the effective speed from this direction. And then we have the frequency and the speed of light. Very useful formula. We'll be using it a lot. The maximum Doppler frequency is when the cosine is equal to 1. So it's the maximum value of the frequency shift is this factor over here, since the cosine cannot be bigger than 1 or smaller than minus 1. So that's called the Doppler spread. And we saw that typical values at 2 gigahertz are on the order of a few hertz if we just have a walking speed, and on the order of 1 or 200 hertz if we have a vehicular speed. Now, even though these Doppler shifts are very small, they're very important because it's reciprocal. It's giving us something called the coherence time, which is essentially the time over which the channel is going to remain more or less constant. So if we have, for example, a Doppler shift of Doppler spread of 10 hertz, that means that the channel, in terms of fading, is going to be roughly constant for about 100 milliseconds, and then it's going to change. So this is a very important notion. And it allows us to classify channels into fast fading channels and slow fading channels. So when this coherence time is long, we have a slow fading channel. When this coherence time is short, we have a fast fading channel. And we'll see that there's pretty distinct ways of studying these classes of channels. So we also saw delay spread. So remember, the temporal shifts, the delays, give rise to this type of situations, right? We transmit a sequence of symbols, each one of duration capital T sub s, symbol time. And so we receive a copy or a replica of this signal over each of these multipath components. So here we have two of them, the nth and the mth component. And as long as the difference in delays is small, for example, that's what we're trying to depict here. We have two different replicas of the signal arriving over paths that are of very similar lengths. So the delay tau sub n and tau sub m are pretty similar. So the relative shift between these two copies of the signal is very small. So when we overlap these two signals, when we combine them, when they combine at the receiver, the resulting signal, the superposition, is going to have pretty much the same shape. There will be a bit of distortion on the edges, on the transitions, but by and large, the shape of the signal, which is where the information is going to be respected. So that situation is what we call a narrow band situation, or a narrow band channel. And the other situation, which we're going to study later today, is the wide band situation, where these delays are actually significant. So for now, let's focus on the case where the delays are small, the difference in delays. So the delays are very similar. And so we can say that the delayed version of the signal with delay n and the delayed version for the component m are very similar. So as a result, we can go back to our signal over here. The low-pass signal is this term in the brackets. And we can factor out these terms, since we can say that all these taus are similar. We can just place them equal to tau sub 0, for example, which is the first arrival. And then, since there's no longer dependence of n, we can just factor this guy out to the summation. which is what we're doing here, right? So we take this guy out, and we're left with this summation of n complex numbers, which are random and functions of time. And so this whole thing, which we're going to call h sub t, is just a random process, right? It's a random quantity that is a function of time. So it's by definition a random process, okay? An equivalent look at this is by means of the impulse response, c, which becomes now a delay at time tau sub 0, a delay tau sub 0, times the same h of t, this random process. So essentially, in narrow band channels, multiplied fading boils down to a constant delay for everybody, and this multiplying factor, which is a random process, h of t. So we can decompose this complex exponential into cosine and a sine, and so we can express this h of t using these real and imaginary parts as an in-phase component and a quadrature component, okay? H sub I and H sub Q. And when the number of terms in this summation is large, we can invoke the central limit theorem and say that these HI and HQ processes are going to be pretty much approximately Gaussian processes. Remember, we talked about the fact that the central limit theorem says that adding a large number of random processes is going to give us a Gaussian random process. Okay? So that's where we got last week. We also covered this figure. Once again, I want to recall these different time scales. We have path loss that changes very slowly over space. On top of it, we have shadow fading, shown in red, which changes faster. And then much faster, we have now this multipath fading. So for example, over a distance of a few meters, the path loss and the shadow fading are not going to change very much. And yet, multipath fading is going to give rise to a very large number of cycles. Okay? So, hoping you get a feel for the very different timescales that these different processes are associated with. So that's where we left in last week. Now we're going to study in a big amount of detail these fading scaling factor h of t, this random process h of t. So the way we're going to study it is by characterizing its mean and its autocorrelation, okay, which are the main quantities in terms of its statistical behavior. So first of all, I'll try to convince you that that even though H is a complex process, we can just study its in-phase and its quadrature component separately, and that's enough to characterize its complex behavior, right? So let's look at the mean. The mean of H is going to be the mean of the in-phase component plus J, which is the imaginary unit, times the mean of the quadrature component, right? So we can study the mean of the in-phase and the mean of the quadrature separately, and that way we can see what the mean is of the complex process. Similarly, although maybe not as trivial, we can expand the autocorrelation of H, which is complex, into a function of the autocorrelations of the in-phase and the quadrature. So maybe I'll go over that on the board. So the autocorrelation of H is equal to the expected value of H conjugate of T times H of T plus delta T. Okay? Now, we can write this as the expected value of the in-phase component. So the H is equal to the in-phase plus J, the quadrature. So since I'm conjugating, I'm going to put here minus J times H quadrature. Okay, so that's the first term. And now I'm going to multiply that by H of T plus delta T. So we have the in-phase plus J okay, so I'm just using the definition of a complex variable. So we have two terms here. Now we can expand these products. So I'm going to multiply each of these with each of that. We're going to get 4 cross terms, right? The first one is going to give us the autocorrelation of the in-phase component over here, right? So we take this term and this term, multiply them and expect. That's the first term over there. Now we take the imaginary part, so j and minus j is going to give us 1. So we get the product of the HQ is going to give us the autocorrelation of Q. That's the second term over here. And now we have two cross terms that are imaginary. This with this and this with this. Okay? When you work it out, they're both actually the same term. So we're going to get 2 times j times the cross correlation between I and Q. Okay? That's how you get there. And so to study the autocorrelation of this complex random process, we can just study the autocorrelation of the in-phase, the autocorrelation of the quadrature, and their cross correlation. Okay? So now we're going to study these 3 quantities, using which we can characterize fully the correlation of the complex process. And a notation on comment here that the textbook uses tau to denote these time shifts in the correlations. I'm going to use delta t to avoid confusing this tau with the delays tau, which are in our formulation. Okay, so all these delays that are here are called tau. So when you go on the textbook, be careful because he uses tau with multiple meanings. Okay, so I'm going to use delta t to indicate these shifts that appear in the correlations. So keep that in mind if you want to reconcile some of the formulas. Everything else, I think it's exactly identical in terms of notation. So for this analysis, we're going to invoke local stationarity. So the number of multipath components, capital N, is going to be constant. The amplitudes, which are the alphas, and the angles, which are the thetas, are going to be constant. Even the speed is going to be constant. So we're looking at a frozen universe where nothing moves. All the buildings, all the objects that reflect the signal are fixed. And the only thing that moves is the receiver. So we have a base station, a bunch of static objects, and our receiver is in a car or somebody walking with it on the street, and it's moving at constant speed. So that's the only thing that's moving in the universe. Everything else is constant. Okay? And we're also going to invoke ergodicity. So the expectations are going to coincide with temporal averages. So let's start by looking at the means, and then we'll look at the correlations. So the mean of the in-phase component, h sub I, let's recall what h sub I was. Okay, it's over here. H sub I is the summation of alpha n of t times the cosine of phi n of t. Okay, so it's this guy over here, and h sub q is going to be this guy over here. So it's one has cosines, the other one has the sines. Okay, so we want to compute the mean of this h sub I. So it's the mean of this summation. We can bring the mean inside, since the expectation is a linear operator. So we have the expected value of a sum is the sum of the expected values. Okay, so we bring the expectation inside. And we have the sum from 1 to n of alpha n times the expected value of a cosine. Okay, the expected value of a cosine is 0. I'm sure you can all see that, right? So a cosine is something like this. So if you look over a long time using ergodicity, the average value is 0. Okay, so this mean is 0. And likewise, for h sub q, we have the same thing as we have sines instead of cosines. Same argument applies, and so the mean is 0. Okay? We'll see later today that when one of the components is much stronger than the others, this may not be true. And let me defer that now because it's kind of a technical point. So for now, let's assume that all the components are similar, so this holds. Okay? Any questions at this point? Everybody following? Okay. Okay, so the mean is easy. Now the correlations are a little more involved. Okay? So let's start with something easy. Let's look at the correlation between HI and HQ when delta t is 0. So they're on the same time. Okay? They're not shifted. So we have the expected value of h sub I times h sub q. Okay? And remember that h sub I is the sum of alpha n's cosines, and h sub q is the sum of alpha n's sines. Okay, so this is in fact, here they are. H sub I and this is h sub q. Just multiply them and expand. Okay? So to go to the next step, what we do is we use the fact that the cross terms where n differs from m are 0. Is that obvious? Or does anybody not see why the cross terms are 0? You all see it? Okay, so the point is that, so all these quantities are independent, right? So the product, the expected value of the product of two independent quantities is the product of the expected values. And we just showed that the expected values are 0, right? So for n and m being different, we can use independence to factor the expectations. And since each of the expectations is 0, because it's just a sine or a cosine, right? We have that all the cross terms where n and m are different are 0 automatically. So we're left with the summation of all the terms that have the same index, right? So the same element here times the same element here. Then it's not so obvious, right? We have a sum of alpha n squared times the cosine and times the sine. Okay, so these are the terms that are not crossed. So they correspond to the same alpha and the same phi. Okay, so this is also 0. And can anybody tell me why this is 0? Okay, so there's a very useful trigonometric relationship that says that the sine of phi times the cosine of phi is equal to the sine of 2 phi divided by 2. Okay, this is a very useful trigonometric relationship. So this product, this sine times this cosine, is just a sine of 2 phi, right? And again, the argument holds, right? So the average of a sine is 0. So this whole thing is also 0. Okay? So we can make a first observation, which is that h sub I and h sub q are 0 mean. Remember, we saw the means were 0. Are 0 mean uncorrelated random processes. Okay? At least when they're not shifted. When they're on the same time, they're uncorrelated. And when they're Gaussian, that means that they're also independent. Remember, the property of Gaussian processes is that uncorrelation and independence are equivalent features. Okay? So now let's study the autocorrelation of h sub I and h sub q. Let's start with h sub I for a certain shift delta t. Okay? Let's study the autocorrelation of h sub I at time t with a shift of delta t. So that's the expected value of hi of t times hi of t plus delta t. Okay? So let's go over this. This one is a little more involved, but not very much. So let's just write down what it is, first of all. So hi of t is just, again, the sum of alpha n times cosine phi of n. Okay? And this is its shifted version, okay? So we just shift t by delta t. So I'm just applying the definition so far, okay? Of this product and the expectation. So let's apply the same trick so far. So let's look first at the cross terms. And again, the cross terms are independent, so we can factor the expectations. And each one is just a cosine, so it's 0 mean. So again, all the cross terms are 0 automatically. So we're left once again with the sum of the terms that are not crossed. Okay, so we have the sum of alpha n squared times the expected value of the cosine phi sub n times cosine of phi sub n at t plus delta t. Okay? So at this point, we can invoke another useful trigonometric relationship that says, let me write it down. So we have the cosine So we have the cosine of A of x times the cosine of y. X and y are two different quantities. Okay. This is essentially the cosine of x minus y plus the cosine x plus y divided by 2. So that's another useful trigonometric relationship that tells us that the product of two cosines, cosine of x times cosine of y, is equal to the cosine of the difference plus the cosine of the sum divided by 2. Okay? Sure that you've seen some of these before. So we can apply this here, okay? And so we can expand this. This is the 1/2 that we have there, the denominator. The sum of alpha n squares times the cosine of the differences plus the cosine of the sums. Okay? Now let's recall what are these phi's. Right? Remember, we saw these phi's have a fixed component plus a component that accumulates over time that has to do with the Doppler. Okay? So let's write this down. Phi n of t is equal to phi fixed plus phi and v sub n. Okay. And we had also phi n of t plus delta t is equal to the same fixed plus 2 pi okay, so we have something like this. Phi of t, phi n of t, and phi n of t plus delta t. Okay, so now we have to look at the differences and the sums and at their cosine. So the difference of these two, you see the fixed term cancels. Okay, this guy cancels. These guys cancel, so we're left only with this term. Okay, so the difference is going to give us a cosine of 2 pi the Doppler times delta t. Okay, that's the difference. And the sum of these two terms is going to give us twice the fixed component over here, plus 4 times the Doppler. Okay, that's the sum of these two. And we have this 2 pi Doppler delta t, which is this last term. Okay? Now, this second term is a cosine of something, some constant plus another constant plus function of time. So it's just a cosine. Okay? So the second term is just a cosine shifted by some quantity, but it doesn't matter because what matters is that the expectation of a cosine is 0. So this whole thing goes away. And so at the end, we'll have with this term, notice this one, why is this one not 0 in average? Anybody? It's a constant, exactly. There's no time here. So that's why. It's not a function of time, it's just a number, right? These are on fixed quantities, exactly right. And in fact, the fact that the correlation does not depend on time is reassuring, since we assumed that everything was stationary. We need to get a correlation that it doesn't depend on time, otherwise it would be contradicting our assumption. So that's a good thing. And we're done, right? The autocorrelation of h sub I is just this summation of alpha squares times the cosine of the corresponding Doppler shift times our displacement. Nice formula. And I'm not going to go over it, but the correlation of the quadrature component is identical. Okay? We're going to start with sines instead of cosines here. And you're going to do the same exercise. And even though you have sines, when you get here, the product of sines, you're going to get cosines of differences again. And it'll take us exactly to the same answer. Okay? So you get the same formula for the quadrature. So now we only need to find the cross correlation. Remember, we found it for equal times. So we find the cross correlation for delta t equal to 0. Remember? And we found it was 0. Now we need to find, for completeness, the cross correlation for arbitrary shifts, delta t. Okay? So I'm not going to go over it, but it's exactly the same process. You start here. Okay? So you have here the cosines and here the sines. You work it out. You're going to get here cosines times sines. There's a similar relationship that's going to tell you how to convert this product into cosines and sines of differences and additions. and you go over it, something will be 0, and you'll find a very similar formula, but now you have a sign. Okay? So this generalizes the result we found for delta t 0. And notice that if you put delta t equal to 0, you get the sign of 0, which is 0, which is what we found before. Okay? So when there is no temporal shift, the correlation is 0 between in phase and quadrature. When they're shifted, then the correlation is given by this summation with the sign function inside. Okay? Questions? Yes?
So the second half is when you're adding
yeah, let me go back. Which term are we computing?
I see how the negatives like cancel out and we'll get cosine. But does that just cancel out because those are because you can't get rid of the time, so it adds together to be 0?
Okay, so the question is what happens here with the different, I'm repeating for the CVN students the question. What happens in this bottom expression? Okay, so the difference, yeah, that's still here, right? So the difference is going to give us that term, right? You see that, which is the constant that stays. In fact, that's the final result, right? The addition of the two phases that we have on the board is giving us this term over here, right? So you'll see that if you add up those two phases, you get exactly what's inside this cosine. Okay. Now, so this cosine is a function of time, and the expectation is 0 because it's a cosine. Right. Doesn't matter that there is a phase shift that's fairly complicated, and there is this fixed component that we don't even know. Doesn't matter because over time it's going to oscillate and has a 0 mean. Right. So that's why. Other questions before we proceed? This is, it's fairly tricky derivation, but I think that once you get a handle on it, it's most of the three correlations are actually found in a very similar way. You have to use 90 different trigonometric relationships, but that's about it. Other than that, they're identical derivations. Okay. So let's now talk about something called the power spectral density for the h sub I and h sub q, and probably you've seen this before in your signals and systems background classes. So the power spectral density of a correlation is just this Fourier transform. Okay, so the Fourier transform of what we just found, we found this autocorrelation of the in phase and the quadrature, and we found that they were identical. So the Fourier transform, which is the PSD, are also identical. Okay, so this is the notion of power over bandwidth usually. And here it has another interpretation that is very useful, which is that we can view it as the PDF, the probability density function, or maybe the histogram of the random frequency shifting caused by Doppler. Okay, so say we send a signal S sub t, which is just a cosine. So we send a signal that is a cosine of frequency f sub c. Okay, if there was no multipath, if there was just the receiver in the universe and nothing else, we would receive a signal with the same frequency. Okay. Now, because of multipath, its reflection comes in with a different Doppler shift. So its reflection, its reflected bounds arrives with a slightly shifted frequency. So the PSD is giving us a histogram of how often we encounter each of these frequencies around f sub c. Okay, and in a little bit we'll see a typical shape of the PSD. But for example, this is let's say this is frequency, okay, and this is f sub c, right? If we had a multipath environment where we send a signal at frequency fc and we get the same number of components at each of the Doppler shiftings, we got something like this, right? Uniform. So if the PSD was uniform, that would mean that we find as frequently a shift to the right or to the left by a certain amount. Okay? As we'll see, typically these are not the shapes that you find, but it is conceivable. So that's it. Yes, questions? That's the Fourier transform. right here. Right? Well, I'll have the equations in a second, but you surely seen this before, right? That's all I want to say at this point about the PSDs. We'll come back to them in the second part of the class today. So let's not dwell on it too much at this point. We'll see a plot that I think will help a lot. Okay, so let's recap what we've seen so far for narrowband channels. We've seen that under local stationarity and with no line of sight component, the in-phase and quadrature components of the fading, h of t, are zero mean and correlated random processes, and we have characterized its auto and cross correlations. Okay, we found that the autocorrelation of I equals the autocorrelation of Q, and is given by this function. And we've seen that the, and I apologize because this expectation shouldn't be here. Okay, so this is a typo. There should be no expectations here. Okay, there should be just alpha n squared times the cosine. So please correct that. Okay. That's what it should be. And we found that the cross correlation between the in-phase and quadrature is given by this function, and it's very similar except we have a sign instead of a cosine, and we have a minus negative sign. Okay? We mentioned that if n, the number of terms in the summation, which is the number of multipaths, is large, the hi and hu are going to be Gaussian random processes, independent. And now to move on and to further elaborate on these expressions, note that these are functions of the alphas and the phis, the thetas. Okay, so the function of the amplitudes and the angles of the multipath components. And so to proceed, we need to specify or postulate specific alphas and thetas. So we need to postulate values or profiles for these amplitudes and angles to get more specific expressions. Okay, so particularly insightful environment that is very often invoked is the so-called uniform scattering environment that was introduced by actually by Clark, but it was popularized by Jakes. So it's often called the Jakes spectrum or the Jakes environment, although it was introduced by Clark. So I'm going to call it the Clark-Jakes uniform scattering. And this is as simple as it gets. So let me draw a picture. Okay, so we have our transmitter over here somewhere. Okay, we have our receiver here. And let's imagine we're seeing this from above. Okay, so we're like we're flying over or something, and we're on top of the receiver. So this environment is one where the multipath components arrive uniformly in angle from all directions and with the same strength. Okay, so remember this is a view from the top, and we get multipath components arriving equally spaced with the same energy and the same strength from radial directions. Okay, so the let's say we postulate an angle that is 2 pi divided by n, and so we're going to have one component arriving here with angle 0, then one component at delta theta, another one at 2 delta theta, another one at 3 delta theta, all the way to we close the circle. Okay, so we're going to have n of these components. So we're going to cover 2 pi with uniform angles. Okay, extremely simple. That's why it's called uniform. And the alphas are going to be the received power. So alphas are going to be the received power divided by n. Okay, same power. And the factor of 2 here is just to compensate. Remember that there is a factor of 2 discrepancy between the passband and the low pass powers. So that's what the factor of 2 is here, but don't pay too much attention to it. Doesn't matter too much. The point is to divide the power equally between these components and to space them equally in angle. Okay? So I hope that's clear. And with this very simple setup, right, we can go back to our expressions, look at these formulas, and just plug in those values for alpha and theta and see what we find. Okay, so let's start with the autocorrelation. Okay, so let's look at this formula, and now we're just going to put alpha n equal to 2 PR divided by n, capital N. That's going to be the alpha square, I'm sorry. So, to be clear with the notation. That's the amplitude square, which is the power. Okay? And the thetas here are going to be this 2 pi divided by n. Okay? So, we're going to get something like this. Exactly. Let's go over it in theta. So, we have suppose the picture is clear in your mind for now, at this point. So we have 1/2, okay, times alpha n squared, which is 2 r divided by n. Okay, so the summation of the cosine 2 pi x d. 2 pi x d delta t cosine of pi n, which is n times delta theta. Okay, so this 1/2 cancels the factor of 2. Okay, and now we can take this equation and plug it over here. Okay, get PR, and here we have 1 over n. So we have divided by 2 pi sum okay, so we get something like this, which should be what we have in the slide. If I didn't make any mistakes. Okay, so that's over here. Okay, we just substituted these values for alphas and for thetas, and we got this. Okay. Now let's allow this capital N, the number of components, to go to infinity. Okay, so we get these. Remember the picture I had with all these components arriving at equal angles. Now let's allow this to get more and more dense, so that in the limit, there are components on every single little tiny direction. Okay, so mathematically, this summation is going to become an integral. Okay, so the summation is going to become an integration that goes over 2 pi, so from minus pi to pi, of the very same function, with now this delta theta. Remember, this is the difference in angle between two components. As the number of components goes to infinity, and they're infinitely close to each other, this is going to become a differential angle. Okay, so we have these conversions into an integral, and this is a pretty nasty integral. It's an integral of a cosine. It's an integral of a cosine of a cosine. Okay, so expanding this cosine as complex exponentials, you can actually put this integral as a function of something called the Besson function, okay, which is this J0. So J0, this is a special function. You can find it if you have MATLAB, for example. It'll compute it for you, or you can go to the web and find tables of it or calculators. It's called the Besson function of the first kind, and order 0. Okay, J0. So if you use MATLAB, it's called Bessel J, and it has two arguments. The first should be 0, which is the order, and then the second should be the actual argument. Okay? So don't worry about this. I mean, this is an integral that happens to give the solution. That's it. We don't need anything beyond that at this point. And this is the expression of the Bessel function of 0 order. Okay? This is integral. So what we can do is plot this function. In fact, we can plot this autocorrelation. So see what we found, right? We found that the autocorrelation of the in-phase and the quadrature components under this uniform scattering environment becomes the received power times this Bessel function. So we can plot this Bessel function. For example, I did this plot myself using MATLAB. Takes just a couple minutes. And it's in blue over here, so it's a ripple function. And I plotted it here as function of the, so this is the Bessel function of 2 pi fd, which is the Doppler spread, times delta t. And I plotted here as function of the product fd times delta t. Okay? Now, I'm looking at the point where the correlation becomes 0. Okay? So why is that point interesting? Anybody has a suggestion? Why it is of interest to see at which point the correlation becomes 0? What does that mean? Which information is that going to give us? Anybody want to venture a guess? Not exactly. So what this is telling us is how much delta t we have to allow for or let pass. So this is time. This is a time shift, right? How much time we have to wait? Okay, so let's say that we take a fading process, right? This random process. We observe it at some point. So we learn its value. Now, how much time we have to wait until the fading has changed so that what we learned before is giving us no information, so that there is no correlation. So what we learned before is no longer relevant, right? For example, imagine we observe the fading when it's in a good point, up very high, right? So it's a very strong channel. Now, how much time we have to allow for so that the channel has changed so that, you know, it can be good or bad. We don't know anymore, even though it was bad before, it was good before. So how much is the memory in some way, right? This is the memory of the system. So the time that the correlation dies off, this is the memory in terms of time. How much time we have to wait so that the fading has changed and is statistically completely independent. Okay, this is an important concept. So are you guys understanding that? Does that help or comments? Yes.
The coherence time is you define it as when the correlation is over 0.5.
That's exactly right. Yeah.
Time where there's completely no correlation between two.
So
Evaluate the channel.
So the comment is that the coherence time is going to be related to this zero crossing, which is exact. So the coherence time is typically defined as the point where it has fallen by half, or by some fraction, but typically it's half. So it will be over here. So the correlation time is a little more extreme. So the coherence time is how much you have to go so that it has changed substantially. So what you learn is just not very relevant anymore. And then the correlation time is when it has fallen to 0, so that what you learn is completely using as outdated information in some way. So they're very similar concepts. Usually one is smaller than the other at this point. Okay, so try to digest this. I know it's a lot of stuff today, so I'm happy to slow down if we have to. This is important stuff, and this is a lot of information that I'm going to throw at you today. So please ask questions if you must. These are important concepts in how wireless systems work. Okay. For example, let me give you an example that maybe you've experienced in the past. Let's think about FM radio. Okay, like in the car, for example. The frequency of FM radio is 100 megahertz. That means the wavelength is 3 meters. Okay? Remember, it's just the speed of light division. Okay, it's 3 meters. So here we're finding that, and I'll go over this in a second, but we're going to find that this the correlation time corresponds to a distance of about 0.4 times the wavelength. Okay, and now I'll go over this in a second with you. So if the wavelength is 3 meters, 40% of 3 meters is just about a meter. So a little over a meter, maybe 1.2 meters. Okay, that means that for the FM radio signal, the correlation time of the fading, the correlation distance is about 1 meter. So that means that if you stop your car at a light, for example, or a crossing or something, and it happens that you're in a bad spot where the signal has died off because of a fade, right? The signal is fading, so you cannot hear the radio very well. If you let the car just roll on for about a meter, you'll see that most probably you'll recover, because you're going to get a completely new channel, a completely new fading. Right? You're going to go this far. You're going to travel this distance. So the fading is going to be completely independent. So if it was bad before, there's a pretty good chance it's going to be good now. And I've tried this myself. So you let it roll just for about a meter. And with high probability, you're going to get a good, much better signal. Okay? So let's go over this relationship between time and space. Okay? So looking at the plot, we can see that the correlation time is about 0.4. Okay, so we need that this product equals 0.4 for the correlation to fall from 1 to 0. So we have that f sub d times delta t should be about 0.4. Okay, now we know that the Doppler f sub d is equal to the speed of motion divided by the speed of light times the frequency of the signal. Okay, so we know this, and we know that the frequency of the signal is equal to the speed of light divided by the wavelength. Okay, these are all basic relationships that we've seen before. Okay, so if we take these two formulas and plug them here, we're going to get that for this product to be about 0.4, we have to travel a distance of about 0.4 times the wavelength. Okay, it's just a matter of plugging these two equations in here and using the fact that and use one more equation, which is that speed is equal to time, space divided by time. The speed of motion is equal to the distance divided by the time. Okay, so using all these relationships, we can map this coherence, this correlation time, into the correlation distance. And so we find this rule of thumb, which is that the fading on the uniform scattering, which is the model we're using now, this Clark-Jakes model, the fading correlates over distances that are about 0.4 times the wavelength. Okay, so the fading is going to change completely as soon as we move a distance of this scale, which is just going to be, for FM radio is about 1 meter, but for our systems at 2 gigahertz, it's going to be about a couple of centimeters. Okay, so it's a very small distance. Okay, let's see, let's cover these. Okay, let's cover these and then we'll take a break so you guys can digest some of these. Let's continue with this Clark-Jakes uniform scattering. Remember, we're still with this very simplified model for this scattering. Uniform from all directions. Okay, so all this is bounded for that environment only. And let's compute the PSD. Remember, these were the power spectral densities were just the Fourier transformations of the autocorrelations. Okay, so we can take this autocorrelation, which is the received power times the Erksm function, and compute its Fourier transformation. And actually, it so happens that the result is pretty simple. It's a pretty nice function, which is up here. So it's in closed form, and it's basically 1 over the square root. So as long as so for frequencies within the Doppler spread interval, it has this shape and it's 0 outside. We know that the frequency can never be bigger or smaller than can never be shifted by more than FD. Remember, this is the maximum frequency Doppler shift. So the shift can never be in either direction, cannot exceed f sub d. Okay, so we can only move up to FD and down to minus FD in terms of shifting. Remember, so 0 in low pass corresponds to FC in passband. So the FC cannot be shifted by more than this quantity. And the shape is like this U shape. So if you got this function, it looks like a U shape. And can anybody answer? So why don't you think, shouldn't this be uniform? You know, we have an environment where scattering is uniform from all directions. And yet, in terms of Doppler shifts, we find that most of the time, the frequency is shifted by FD or minus FD. See, most of the area, so the probability is on the extremes. So there's very little here, right? So most of the time, the frequency is shifted all the way into either direction. And yet, the environment is uniform, scattering from all directions. So, anybody wanna make a guess as to why we don't have a uniform PSD? Anybody has any ideas? Well, here's the answer. The answer is the cosine. So even though the thetas are uniform, right, they appear in the correlation to the cosine. Let me see if I find a good one. Okay. So even though the thetas are uniform from 0 to 2 pi, they appear here. What appears here is not phi. What appears here is not theta. Is the cosine of theta. So even though the angles are uniform, the cosines are not, right? The cosine has a shape like this. See, wireless communications in action. So the answer is the cosine. Okay. If this was a function of theta, it would be uniform. But it's a function of the cosine of theta, which changes the shape. So actually, you can try this with MATLAB, for example. If you plot 1 over the cosine, plot this function, 1 over the cosine of theta, for theta going from 0 to 2 pi, okay, you're going to find a function that looks like this. It's like a U function. Okay, so you can try this. It just takes a minute with MATLAB. So that's the reason. The cosine function is what gives this very interesting shape, where most of the time the shape is on the extremes and very rarely on the middle. Okay, let's take a break here. Okay, I will continue at 5:30. Okay. So now in the break, I just had a visualization of how ubiquitous wireless is. There was, at some point, there was 7 of us in the corridor, all on cell phones. So 6 of you plus myself on cell phones. So it's really no, we did the count. It was much higher. It was like 90%, probably 100%. Okay, so let's continue. And as I was saying before, this is pretty important material, and I think that you have to digest it a little bit. Hopefully the homework is going to help you a lot. And next week, come to office hours if you have to, because it's a lot of stuff. And I think that one has to play with the homeworks to get a feel for the quantities and all that. So let's proceed, and please ask questions as much as you have to, okay? So we talked about correlation. So we studied the statistical properties of the fading process in narrowband channels, and especially for this Clark-Jakes uniform scattering environment, we found this nice expression for the autocorrelation of the I and Q components, just this Besson function, okay, which moves like this. And so it gives us a good feel for how much time or distance we have to let go so that the random process is going to change and decorrelate itself. Okay, it's a very important quantity. And we'll talk about diversity in about 3 or 4 lectures, and you'll see that we'll come back and revisit some of this stuff. So let's now talk about the amplitude and power distributions. So now let's look at this random process that changes over time randomly, okay? And let's say we wait for a long time and we see as it's changing up and down, fading, and we plot a histogram, okay? We want to plot a histogram of how often we find good channels and bad channels, and how often the amplitude or the power are high or low. And so we want to study the distribution, okay, of a particular point in time, how frequently it's high or low, okay? So we want to look at the distributions of the amplitude or the power, which is just the square of the amplitude. So under the central limit theorem, we've seen that Hi of t and Hq of t are Gaussian random processes because we have the sum of many components. So they're zero mean Gaussian random processes. And a property of complex random variables is that if you have a random variable whose real part is Gaussian and whose imaginary part is Gaussian also, the amplitude, which is the square root of the square in phase plus the square curvature, has a distribution which is called the Rayleigh distribution. Okay, this is a very important distribution. We're going to be seeing it very often because thanks to the central limit theorem, it is often true in practice that these processes are close to Gaussian, and so the amplitude is close to Rayleigh. Okay, so the PDF of a Rayleigh random variable looks like this. Okay, so we're using here z to denote the amplitude, and so the PDF of z is given essentially by an exponential of minus z squared. So PR here, let's go over each quantity. PR is the average power due to path loss and shadow fading. Okay. On top of this shadow fading, there is going to be this Rayleigh fading, this multipath fading, with this distribution. And so it's an exponential to the minus z squared divided by the average. And here we have 2 times z outside. Okay, again divided by the average. This is the Rayleigh distribution. And take note of it because you'll be using it a lot. So that's the amplitude. And when the in-phase and quadrature components are Gaussian. And the square of the amplitude, which is the power, has an exponential distribution. Okay, just exponentially decaying with PR again being the average power. Okay, and again average power due to path loss and shadow fading. So that's the amplitude, or its square, which is the power. Now remember that the characterization is in phase and quadrature, or amplitude and phase. Okay, so the amplitude is here, and in the case that these are Gaussian, the phase is uniform. Okay, it's uniform between minus pi and pi, or between 0 and 2 pi. So you can take all these values between minus pi and pi with equal probability. Okay, let's go to a quick example. Let's say that the receive power, average receive power due to path loss and shadow fading is 20 dBm. Okay? So that means how many milliwatts? Anybody? Quick? 100 milliwatts? Exactly. So what's the probability that the receive power due to multipath fading falls below 10 dBm? Or in other words, how often, when the average is 20 dBm, how often is the instantaneous value below 10 dBm? So the way to find this is we integrate between 0 and 10 the PDF of the power. Okay, so that's the probability that the power is between 0 and 10. It cannot be, in reality we have to integrate from minus infinity to 10, but the power cannot be less than 0, so we can just integrate from 0 to 10. Okay, so this integral can be very easily solved by hand, and you'll find that the answer is 9.5%. Okay, so even though the received power average, accounting for path loss and shadow fading, is 100 milliwatts, about 9% of the time, because of fading, of multipath fading, is going to fall below 10 milliwatts. So let's recover an old picture. Okay, so this is good. So we're saying, even if this red line is 20 dBm, if we look at 10 dBm, we find that about 10% of the time, some of these deep fades are going to fall below 10 dBm. Okay, 9% of the time, to be precise. This particular example. Questions? Is that clear? We're doing this for the homework, so it better be. Yes.
Using the z-squared.
Yeah.
I'm not sure.
Yeah. The question is if I'm using the z-square or the here, right? You mean this z-square? Yeah. So the question I'm asking is about powers, right? So I'm using this expression over here. Now I could formulate the same question with amplitudes, right? So how could I do that? And it's a very good question because it allows us to relate the two expressions. So we're saying that the received power is a bar is equal to 100 milliwatts. Okay? And this is 0.1 watt. Okay? So what's the amplitude that corresponds to this power? It's the square root of this, right? So the amplitude, let's call it A, is equal to square root of 0.1. Okay? Which is about 0.3, something like that. Okay? So I can formulate the same question using amplitudes. So if I want to ask the question, how often is the received power, remember, we want to say, okay, how often is the received power, let's call it z squared, less than 0.1 watts. Okay? So this is our question. How often is z squared less than 0.1 watts? We can formulate a similar question saying, okay, how often is z less than square root of 0.1? Okay? These are equivalent questions, right? How often is the power less than 0.1 watts? How often is the amplitude less than the square root of 0.1? Since this amplitude is the same, corresponds to this power. So if I formulate the question using powers, I can use the exponential distribution on the right. And if I formulate the question using amplitudes, I can use the left-hand expression for amplitudes and get a similar integral using that expression. And you'll find that the answer numerically is the same, 9.5%. Okay? Okay, so the Rayleigh fading is a very nice distribution because it's mathematically simple, and in practice it is very often encountered. So people do make measurements and they find that the amplitude is actually Rayleigh and very close to Rayleigh. Now, sometimes it happens that there is a dominant component, the linocyte component, the one that goes directly without any reflection, that is much stronger than the other ones. and then the receiver can actually lock onto its phase. So even though this is a cosine, the receiver can actually track this cosine and sort of cancel out its variations. And so we get something that is no longer zero mean. And the book has an explanation, a little more detail on why, mathematically, why this is true. I won't get into it. It's a bit technical, and so you guys can look at it, and if you want, you can come to see me next week. But it is not that important to us. The point is that when there is an iron side component, typically the receiver can lock into it, and the signal is no longer, the random process, it may no longer be zero mean. So in that case, we'll find something like this. We'll find the superposition of a random part, which is zero mean, which is the summation of all the components except for the minus side. Okay, so that's what I'm indicating here. The summation for n bigger than 0. Remember, I was using n equal to 0 to indicate the minus side component, and then n equal 1 to capital N to all the other ones. So the superposition of all the components that go from 1 to capital N, which are the non-minus side, is going to give us a zero mean random process, like the one we've seen before, rarely faded, typically. And then we have the minus side component, which is going to be deterministic, essentially. And so everything we said so far still holds for this random part. Okay, so the random part is going to be under the CLT, central limit theorem, is going to be rarely faded. So all these formulas work for the random part. But on top of it, there is this deterministic component that has to do with the minus side. Okay, so we'll find that if n is large, we have a complex Gaussian random process that is no longer zero mean. So we have a complex Gaussian random process with a certain mean determined by the minus side component. So this gives rise to the so-called Ricean distribution, which was first characterized by Stephen Rice. That's why it has this name. He was a researcher at Dunlop's in the 1950s and 60s. And the PDF that we had here before for the amplitude, in the case of Rayleigh, becomes this expression significantly more complicated. Okay, and is a function now of this k, which I'll describe in a second, and it uses, it relies on a modified Bessel function. Okay, so this I sub 0 is closely related to the j sub 0 we saw before. It's a modified Bessel function. It is an integral that I don't have it here. I think it should be in the book probably. But it's one of these special functions that MATLAB has, or that you can find on the internet. And that's this function over here. And then we have this usual exponential. Everything else looks like Rayleigh, but we have this additional modified Bessel function. And this k, which is the ratio between the power on the minus side component and the power on all the other components. Okay, so remember these alphas are the powers. Okay, these alphas are the powers of the different multipath components. So we look at the power of the minus side component, which is the one where n equal to 0, and we divide it by the sum of all the other ones. That's called the Ricean k factor. Okay, and this k factor, so is the ratio between the power in the minus side component and the power in all the reflections. And this factor measures the severity of the fading. So let's look at some extremes, okay? If k is 0, right? Let's go back here. If k is 0, it means that alpha 0 is 0. So it means there is no line of sight. Okay? So if there's no line of sight, we just have a Rayleigh fading. Okay? So in the case that k is equal to 0, the Ricean distribution becomes the Rayleigh distribution. In the other extreme, as k goes to infinity, we find that, okay, let's go back. If k goes to infinity, it means that this whole thing is going to 0. Okay? Which means that we only have line of sight. There's nothing else. Okay? And if there is only line of sight, so we go back to this idealized setup where there is nothing in the universe, there's no reflections, there's only the line of sight. So there is no fading. Okay? So for k going to infinity, the Ricean reverts to a channel with no multipath fading. There is only path loss and shadowing. So these are extreme cases. And then for any k in between, it's going to be a different distribution. For large k is mild fading, and for small k is more severe fading. And for k equal to 0 is the most severe fading, which is Rayleigh fading. Okay, So this is the second distribution we're going to deal with, Ricean. And there is a third, even more general than the Ricean, which is the Nakagami distribution. And this one was designed to feed empirical data from actual measurements. And it has also pretty complicated PDF over here. So it's a function, instead of the k factor, we have now this m factor, this m. And this gamma is another special function that you can find on the on MATLAB, for example, on the internet. It's called the gamma function. And this m is the fading parameter. So Nakagami reduces to Rayleigh and Ricean for certain values. So for m equal to 1, Nakagami becomes Rayleigh. And for m equal to k plus 1 squared divided by 2k plus 1, then Nakagami becomes Ricean with this particular k. Okay? So we have Rayleigh fading is the simplest. Then we have a more general one that is Ricean that can become Rayleigh but can also be something else. And then we have the Nakagami that can become Rayleigh and Ricean, and for other m's, it can give other distribution shapes. Okay, there's something that's covered in the textbook that I'm not going to get into, which is the neuron crossing rates. So one can actually study these distributions and find the expressions for the frequency with which the fading crosses a certain level. Okay, so very quickly. Okay, so imagine this figure, right? You look at this fading process, and you say, okay, so how often is this fading process crossing a line over here? Okay, imagine that you pick a certain level, minus 20 dB or something. You say, how often on every second is the fading going to cross this line? So you can actually find expressions for what's called the neuron crossing rate. Okay, so I'm not going to get into that. I want to ask you about it, so this optional material. And that's the end of the narrowband channels. So in the remaining of the session, we'll try to cover the wideband channels. But first, let me see if there are any questions for the narrowband fading. Because the wideband is much tougher, so. Okay, so let's get on with the wideband and we'll see how it goes. Okay. Okay, let's recap a little bit. We saw that the definition of a narrowband fading channel was when all these multipath reflections arrive with similar delays. So when we combine them, when they combine, they get superimposed at the receiver. The shape of the resulting summation is pretty much the same shape of the signal that was transmitted. Okay, so we had these delay differences being very small. That was for the case of narrowband channels. Now we're going to get into wideband channels where this is not true anymore. So let's imagine two particular multipath components. Okay, this one and this one, and you can see that the delay shift is now pretty significant. So in this case, the delay difference is at about half of this symbol duration. Okay, this is the symbol time, and just about half of it is the delay of this second component. Now we add these guys up, we get something like this. Okay, I did this by hand, but it's pretty much what you would get, right? So as you can see, the shape of this is completely different from the shape of the original pulse. So the information that was here now, it's still here, but you know, it's highly distorted. Okay, that's what's going to happen in wideband channels. As soon as these delay differences become about 5 to 10% of the symbol duration of the size of these pulses, we got significant distortion. Okay, and this is called intersymbol interference distortion. Why? Because what's happening is that if you think about this being, this pulse is one symbol, second pulse is the second symbol, this is another symbol. So the second symbol, the second symbol here is now interfering with the first symbol. You see, the first symbol here is delayed, and so it's overlapping partially with the first symbol, and so these two guys are actually distorting each other, and we get here some reshaped waveform. So these delays cause consecutive symbols to interfere with one another. And so that's why this is called intersymbol interference, or ISI. That's the main premise of a wideband channel. It results in intersymbol interference. So whereas in narrowband channels, we had this pretty simple model where the multipath propagation resulted in a constant delay for everybody, and this random process, h of t, that was multiplying the signal. So that's what we had in the narrowband case. We had h of t, we had the delay, harmonic delay, and then multiplication by h of t, which was the fading. Now we have something more complicated. We have a multiplying factor at every delay up to the last arriving component. And so we have something like this, right? Instead of having just one delay that fades over time, this is the impulse response. So instead of being just one delay fading over time, now it's going to be a multiplicity of delays. So what tends to happen in practice is that you have clusters of multipaths. So let's look at this picture. You often have a bunch of reflections over here that are coming from objects that are in the vicinity, in some vicinity. So I'm showing this in red. And these multipaths are going to be of very similar lengths, okay? And so the delays corresponding to signals arriving over all these red paths are going to be very similar, okay? We're going to have a second cluster of reflections over here. And again, the delays of all these paths that are shown in green are going to be very similar. For example, this could be some a block of buildings away or a hill or something. So it has multiple reflections that they're all very similar in terms of length and so in terms of delay. And we have another cluster here in blue from some other direction. And the red paths are mutually similar, but very different in length from the green and the blue. So we're going to end up with something like this. We have a cluster of rays of multipaths that arrive around this blue, this delay tau sub 1, and they're going to get superimposed and create fading here at this delay tau sub 1. We have a cluster of reflections, the ones in green, that arrive with a longer delay, but very similar between themselves. So they're all going to combine and give fading here at delay tau sub 2. And yet another cluster at tau sub 3 that are going to also superimpose and create fading at delay tau sub 3. So here, I'm just trying to imagine that this is an animation. So over time, each of these arrows, which symbolizes one delay, is fading because its multiple components are overlap. Okay, but the three clusters are pretty distinct in delay because these groups of objects are at very different distances. Okay, and as usual, we're going to invoke local stationarity, where the average powers and the delays. So at each delay, things are locally stationary. Is this clear as a scenario or not? So you can regard each of these as a narrowband channel. So in this case, we have three narrowband channels. One at delay tau 1, one at tau 2, and one at tau 3. So each one is narrowband because the corresponding composing paths are very similar in delay. But there is big differences in delay between the ones in green, red, and blue. And so we have, in this case, we have three narrowband channels with pretty distinct delay. That's the new ingredient here. There's more than one of these clusters. Yes? Yeah, so exactly. So the question is, first we have to worry about combining the narrowband channels, which we studied in quite a lot of detail. Now we have to see how we handle these different delays. So that's what we're going to see in the rest of the lecture, exactly. So you can, it's very useful to regard each of these three as a narrowband channel. But now how do we study the superposition of three that are delayed with significant delays? Right? It's much more tricky, in fact. But we'll try. So let's go to the limit of a large number of components, okay? Where things are a little easier. And let's say there's no line of sight. So we have similar components, a large number of them. So this will have two consequences, right? The first is that the fading of each of the narrowband channels is going to become Gaussian, right? I mean, the random processes, we have here 3 of them, Gaussian because of center limit. So each of these can be rarely fading. Okay, that's the first consequence, if there is many components. Now the second one is that we're going to get clusters everywhere, right? If really we have lots of components, lots of clusters of components, so not only will each of them be rarely faded, but there's going to be many in between. So it's going to be one here, another one here. So this is going to be populated everywhere. So in the limit, this is going to become some continuous function. So at every delay that you look at, there is going to be a cluster appearing at that delay. And not only that, that cluster will have many components, and so it's going to be rarely faded. So this impulse response becomes now, in the limit, it becomes continuous, as opposed to being a bunch of discrete. So this capital N that we had in the summation goes to infinity, and so we have an infinite number of components. So imagine this as a continuous function of delay, and it changes over time. So it's a function of delay and time. So at each delay there is a power, and now this whole thing is oscillating. Okay, so these are 2 pictures of it, and imagine visualizing like a movie where each of these points in this curve is moving up and down with fading. Okay, that's what I'm trying to convey here. So this impulse response is a zero-mean complex Gaussian random process. And it's now continuous in delay as opposed to discrete, because we let the number of components go to infinity. So let's do the same thing we did for the narrow one, or let's try, and study its autocorrelation. Okay, the mean is trivial is 0, since we said that by construction this was 0 mean. So we only need to study this autocorrelation. And now we have the autocorrelation of a function that of an impulse response that is function of delay and time. So the autocorrelation is a function of 2 delays, tau 1 and tau 2, and a time shift delta t. Okay? So it's the expected value of c at time t and delay t1 times c at time t plus delta t and delay tau 2. So the expected value of this product is the autocorrelation. Yes? C is the impulse response. So the received signal is a convolution of C with the transmit signal, right? And this is a low pass equivalent, right? So we had we're calling U of t the low pass transmit signal. So convolution with C of t tau is giving us the output, the received signal y of t. This is in low pass. Okay, and in the passband signals are, remember, R of t, received signal, is the real part of y of t e to the j 2 pi fct. Okay, and similarly, the transmit signal s of t is the real part of u of t times to the j 2 pi fct. Okay, so just to recap who is who. So this is the autocorrelation of this time-varying impulse response, and it's a function of 2 delays that we pick, tau 1 and tau 2, and a time shift that we pick delta t. So it's the expected value of the product of C at time t and delay tau 1 times C at times t plus delta t and delay tau 2. Now, this goes pretty messy because it's a function of 3 different variables. Now, luckily for us, we have a property of actual channels that says that the response at different delays, tau 1 and tau 2, is uncorrelated. And physically, that's quite sensible, since you can think that, remember that what happens at delay tau 1 has to do with reflections on these blue objects over here. What happens at delay tau 2 has to do with reflections over these objects over here, the green. So these are objects that by definition, since the delays are different, by definition these are far away objects. And so what happens over here has nothing to do with what happens over here. And that's actually the case. So luckily for us, whenever tau 1 and tau 2 are different, there is no correlation, and so the autocorrelation is 0. Right? This guy is 0 whenever tau 1 and tau 2 are different. Okay, that's a good news for us because it means we can just focus on the case where tau 1 is equal to tau 2, and let's call that tau. So now instead of having 3 variables, we have just 2. Okay, we have the autocorrelation as a function of tau and delta t. Everywhere else, so whenever tau 1 and tau 2 are different, this is 0. Correlation is 0. Now let's study the correlation when the taus are equal. So the autocorrelation of tau delta t is the expected value of the impulse response C at time t and delay tau times C at time t plus delta t and the same delay tau. Okay, so we're looking at the point here in this response. We pick a tau, a delay tau, and we see how this function at 2 different times, t and t plus delta t, is related. And the combination of these, so this property that different delays are uncorrelated is called the uncorrelated scattering property, and it was postulated by Bellor in '63. And so we combine these with the White-Stein stationary assumption that we always make. We have this long word and jargon, but this is actually found very often in the literature, which says that the channel is WSSUS. It's White-Stein stationary and correlated scattering. Okay, so you may see this in the textbook. It just means that this condition is satisfied, and we always assume that. Yes.
So if you have different, the reason why it matters that tau is the same is because you want to see what signals you're combining with the right band at the same time. Which ones are going to overlap? Is that what you're saying? Or I'm not exactly sure why we cancel this. Or why it's 0 if you have a different.
Okay. So the question is why the autocorrelation is 0 whenever the taus are different, right? Okay. So this is, first of all, this is an assumption that was made by that guy, and that then experimentally it was verified by just making measurements and computing the correlations and on the data that was measured. So the explanation I have for it is the one I told you before, that different delays correspond to objects that are far away from each other. So because if the objects were close to each other, the delays would be similar. So by definition, now there is a caveat here, right? Because you can in theory have 2 clusters that are far away, but that result in the same delay. For example, and this is a very good point. So there are cases where these may not be true. And we can build one case very easily, right? So we have transmitter here, receiver here. And let's say we have one block of objects here, another one here. And these reflections right? So you can postulate something like this, where everything is symmetric. So these 2 objects are the same distance. One is to the right, one is to the left. And so this group of reflections arrives here. This group of reflections are right here. And these are independent objects. And yet they arrive at the same time. Okay? So the fact that there is a one-to-one mapping between distances and delays may not hold. But what does hold usually is that delays that are very different correspond to reflections on objects that are typically not close to each other. Because if objects are close to each other, the corresponding reflections are going to arrive at about the same time. So they'll fall within this, they're going to fall within the same narrow band delay, if you will, right? So typically, delays, reflections that correspond to distinct delays are going to be different objects, and so their statistical properties are going to be independent, just independent. That's all we're saying, and as a result, the correlation is going to be 0. So that's the US assumption. And so we're here. We got to this point where we only have 1 tau. And so now we want to study this quantity. We want to study the correlation as a function of tau and delta t. Okay? This expectation. Now, to focus it a little more, let's study this autocorrelation when delta t is equal to 0. Because that's the most interesting case. So the autocorrelation at delta t equal to 0 is called the power delay profile. And now it's just a function of tau. Okay, so we went down from 3 variables to 2. And this determines the signal power received at each delay. Okay, so this is the typical, let's go back here. Okay, so we've got this function, and we say, okay, at each delay tau, how much power is there? In other words, each of these clusters, how much power is reflected by each group of buildings, by each group of objects that result in one of these delays. That's what this function characterizes in the limit of an infinite number of objects, when everything is continuous. This tells us how much power is received at each delay. Okay, so imagine we send a signal that is infinitely short in time, just a very short pulse, very, very short. Okay, pump. We just send that. Now, what do we receive? We receive something like this, right? We receive, because of reflections in different objects, we receive the signal that is, even though what we sent was infinitely short, we receive something that is now much longer, because one reflection arrives first, then another one, then another one. So the question is, how much power arrives at each delay? That's what this function is going to tell us, the power delay profile. When we sum over all the delays, we're going to get all the power that we receive. Okay? But some will arrive first, then some later, depending on the corresponding reflection. And there are 2 quantities are used to characterize this function. So we can just give the whole shape. We can just, study or measure the whole shape of this function. And this is done actually. So the way you measure this is exactly as I told you. You go in the field, you send very short pulses, and then you receive them, and you measure the power received over time, and you plot a function like this. Okay, so you can find that in the textbook. So to abstract this function into a couple of numbers, usually what we study is its delay and its deviation. So the delay, the average delay, let's normalize things so that the first arrival, when the first component arrives, that's time 0. That's delay 0, just by definition. Let's say that's delay 0. Now, we'll keep receiving power for quite a while as all these reflections come to us. And so we ask the question, what's the average delay of all this stuff we're going to receive? So starting from the moment we get the first component, what's the average delay on which all this power is going to arrive? So we're going to call that mu sub t. And we compute it using this expression. Okay? It's essentially an expectation scaled by the total power. That's what it is. Okay, so that's the average delay. For example, for this particular function, where the delay profile has this shape, mu is going to be just about here. Okay, so we get the first arrival here, and last arrival here, and the average delay is going to be somewhere in here. Now, we can use all this formulation to define the delay spread in a very precise manner. So I already defined last week the delay spread as roughly the difference between the first and the last arrival. Okay, so what I told you, this is the first arrival, this is the last arrival, the delay spread is roughly the size of this function. Okay, now I'm going to give you a more precise definition of the delay spread. which is this equation over here. So this is it's called the RMS, or root mean squared delay spread, and it's the standard deviation of the delay around the mean. So standard deviation of this function around its mean value. So let me use a plot. Illustrate this. Okay, so I'm going to plot two different functions, two different power delay profiles with the same mean, or mu sub t. Okay, so one will be this. Okay, so these are two different functions, two different power delay profiles, right? So this is power versus delay, and I've plotted them so that they have the same average delay, called mu. Okay, but they have very different delay spreads. So which one has a bigger delay spread, top or bottom? Okay, right? So even though they have the same average delay, this one has a much bigger spread of delays over time, and this one has a very small one. Okay, so that's what this quantity is going to tell us. This sigma is going to tell us. So the square of the sigma is the variance. You can think about it that way, and this is the standard deviation. So this tells us how much the delay typically departs from mu. So here is going to be just about this much. Okay, and here is going to be just about this much. So let's go through a couple of examples. Let's say that the power delay profile has an exponential distribution, just this formula over here. This is actually a model that is used very, very often because it's very simple. So this will move from something like this. It would be some initial delay, let's say 0. And then it just follows exponential forever. Okay, so we keep receiving power forever. That's this exponential function. So in this case, there is a nice property that if you compute the mu using this equation, okay, and the RMS delay spread using this equation, you'll find that they're actually equivalent. So these exponential profiles are used very often because they have this property. So the mu is over here. And standard deviation, the delay spread, happens to have the same numerical value. So this is 10, right? The deviation is also 10. So it's going to go actually all the way over here. That's why these exponentials are very popular. And another one that's used commonly is the exponential truncated. Right? The problem with this is that in theory you keep receiving power forever, up infinitum. So people usually truncate it and say, okay, so we're going to receive power, we're going to exponential increase over time, and then at some point we just truncate it to 0. So we have here a numerical example taken from the textbook. If we keep receiving power within a window of 20 microseconds, okay, exponentially decaying, and then we get 0 after that. The average delay is going to be 6.87 microseconds, and the delay spread is 5.25 microseconds. Okay, so this tells us that in this channel, if we send a tiny short pulse, extremely short, like zero duration, right? We'll receive power for 20 microseconds. Okay, first very strong, and then it's going to fall exponentially over time. And at 20 microseconds, we'll stop receiving power. Okay, that's the response of the channel. And so the average delay is about 6.8 milliseconds. and the delay spread is just over 5 microseconds, and the delay spread is just over 5 microseconds. Okay. All right. Questions with the delay spread? Yeah, you can. Okay, the question is if the delay spread is like the bandwidth. Now we'll see exactly how to interpret it in the frequency domain. So it has a bandwidth interpretation, which we're going to cover that exactly. So it's very useful to look at things in the time domain and in the frequency domain, and we'll do that now. So here we've seen things in the time domain, and now we're going to look at it in the frequency domain, exactly, and then try to reconcile both points of view. So the bandwidth we're talking about is the coherence bandwidth, which is what we're gonna cover now. And I know this is a lot of stuff, guys, but we're almost done, so bear with me, and then we can digest this during the week. So indeed, let's get some additional insight by looking at things in the frequency domain. Okay, so how do we go to the frequency domain? Well, we take a Fourier transformation. Okay, so we take this time-varying impulse response, C, and we compute its Fourier transformation with respect to tau, which is this transformation. And we get capital T, that's capital C, which is now a frequency response, so it's a function of frequency, and it's also a function of time. Okay, so this is the response at time t and frequency f. Now, if needle C in the time domain was a Gaussian process, as often we've taken it to be, then capital C is also a Gaussian process because Fourier transformation preserves Gaussianity, so that's good news for us. And furthermore, if needle C was White-Stein stationary, as we always assume it to be, then capital C is also going to be stationary. So that's also good news. And now let's look at the autocorrelation at two frequencies, F1 and F2. Okay, so let's look at the correlation between this C at frequency F1 and C at frequency F2 with a temporal time delta t. Okay, so we'll look at C of t F1 and C of t plus delta t F2, and expecting the product, we can get this autocorrelation. Now, usually we just want to care about the case where delta t is equal to 0. Okay, so we just want to study this when delta t is 0. So we want to study how two different frequencies, F1 and F2, are correlated at a particular time t. Okay. So this is the computation. I'll take you through it. It's actually easier than it looks like. So just recall this expression. Okay. So capital C is this Fourier transformation. So we're just going to take this integral as it is and plug it over here. Okay. So this is capital C at time t and frequency f1, and this is the same integral. No, this is the same integral twice, except here we have and I'm sorry guys, but this should be f2 here, also here, also here. I apologize. So this should be f2 here, here, and here. Here it appears. Let's fix that real quick. All right, never mind. I'll do it later and post the slides corrected. But bear with me. This is F2, also F2 here and F2 here. Okay. So we take this is capital C at time t and frequency F1. This is capital C at time t and frequency F2 should be. Okay. And I'm using the, tau prime to indicate the integration variable because it's a different one. We can bring both integrations together. Okay, so here there are two steps. First, I bring both integrals together, and then I bring the expectation inside. Okay, I can always do that. I end up with this. Now remember we said that middle C was uncorrelated unless the taus were the same, by assumption. So we get here a delta function. So it's only non-zero when tau and tau prime are equal, otherwise it's 0. And this is actually what we found before. This was the autocorrelation that we found of middle C, which we computed before in the time domain, under all these assumptions. Okay, so we substitute that in here. And now what we do is we have an integration that has a delta function. Okay, so this delta function comes in integration. And so we just move stuff around and we end up with this. Okay. Now the second integration, as you probably know, the integration of a delta function times another function is going to give us the second function evaluated at tau. Okay, it's the property of the delta function. When you integrate, it just samples the function for you, and so we get these. Remember, this should be f2, so we get f2 times tau. So we get this. Okay, and now we're set. Now all we do is we define f2 minus f1 to be delta f. Okay, which is the frequency difference. So we find that the autocorrelation of the frequency of the response at two frequencies f1 and f2 is equal to this integration, which is just the Fourier transformation of the autocorrelation of little c. Okay, so we found that the autocorrelation of big C, which is the frequency response, is equal to the Fourier transformation of the autocorrelation of little c, the power denied profile that we studied before. Okay, this guy over here. So what we found before, we just Fourier transform it, and we get the autocorrelation of two frequencies spaced by delta f. And so these allow us to define the notion of a coherence bandwidth. So this correlation of capital C expresses the correlation of the channel at two different frequencies separated by delta f. So how much delta f do we need? So how far apart do the frequencies have to be such that the autocorrelation is about 0? Remember, it's the same argument we used before for the Besson function. How far we have to go in time or in space, in this case in frequency, so that the correlation falls to 0. That's the correlation, that's the frequency interval over which a channel is uncorrelated. And that's by definition the coherence bandwidth. Okay? So recall a basic property of the Fourier transformation, which is that if a signal has a certain duration in one domain, its Fourier transformation has duration 1 over that. Okay? So if you have a frequency of time, a function of time that has duration, so it's 0 everywhere except for a certain interval of duration t, okay, the Fourier transformation of this is non-zero over an interval of frequencies which is about 1 over t, okay, roughly speaking. It's a property of the Fourier transformation. And so we saw that the power denied profile, okay, we saw that the power denied profile, the duration was essentially what we computed as a denied spread, okay? So its Fourier transformation will have a duration which is roughly the reciprocal of the denied spread. So roughly, and roughly means within a constant, the coherence bandwidth is roughly the reciprocal of the denied spread. Okay, so that's your notion of frequency, of bandwidth associated with the denied spread. So let's go back to this example we saw, right? We saw that we had here for this exponential channel, we had a denied spread of about 5 microseconds. It's a pretty typical value for like suburban environments. So the coherence bandwidth of that is roughly going to be 1 over 5 microseconds, which is 5 megahertz, roughly speaking. So for this channel, if you take one frequency and you want to say, okay, how far do I have to go in frequency so the channel is completely decorrelated, so the fading is completely independent? You have to go about 5 megahertz away, okay, for this channel, which is pretty far. Yeah, that's quite a lot. So that's the notion of a coherence bandwidth. So in the narrowband case, we found that by definition, narrowband channels were those where the denied spread was much shorter than the symbol duration. Okay, remember that the pulses have to be all pretty much lined up. So the difference in delays, which is the delay spread, has to be much smaller than the symbol duration. And so since the delay spread is 1 over the coherence bandwidth roughly, and the symbol time is 1 over the bandwidth of the signal roughly, we find that the coherence bandwidth has to be much bigger than the bandwidth of the signal for the channel to be narrow one. Okay, so these are dual conditions. In the time domain, a channel is narrow one if the delay spread is much smaller than the symbol time. In the frequency domain, a channel is narrow one if the coherence bandwidth is much bigger than the bandwidth of the signal. See, these are completely equivalent conditions. And so, because of that, narrow band channels are often said to be frequency flat. Because what happens is that fading is correlated over the whole bandwidth of the signal. So, if you take your signal, so we're going to be sending, remember, these pulses, okay? Pulses of duration is a pass, okay? And for the narrowband channels, we want that the delays of all these pulses arriving over different paths are very small. The difference in delays, so that all the pulses are pretty much lined up. Now, in the frequency domain, the Fourier transformation of this pulse is going to be some signal in frequency, okay? And in the condition in the frequency domain is that the fading over this whole bandwidth has to be correlated, okay? So the fading has to be about the same on all the points of bandwidth of our signal. That's the frequency domain condition for narrowband channels. And so that's why we say that in narrowband channels, the fading is frequency flat, because the whole bandwidth of the signal fades together. In wideband channels, that's not the case. And so we have that the signal is comparable or even bigger, the bandwidth of the signal is comparable or even bigger than the coherence bandwidth. And so we have that different parts of our signal in the frequency domain are going to fade separately. So we send this signal in the frequency domain, and some part of it is going to fade down, another part is going to fade up, and so the whole thing is going to be reshaped. Okay? There's a very useful figure in the textbook, figure 3.13, that illustrates this point. So take a look, please, after the lecture, and it'll help you clarify this point. Okay? So let's go through an example. Let's say we have an indoor delay spread of 50 nanoseconds, which is a typical value for a room like this, for example. What is the maximum symbol rate that we can use such that the intersymbol interference is negligible? Okay, so that means that for ISI to be negligible, we want that the channel to be narrow one. So we want what's the maximum symbol rate we can use, or what's the smallest symbol time T sub s, such that the channel is going to be narrow one. So how short can we make the pulses so the channel is going to be pretty much narrow one? Let's assume that short means a factor of 10, or long means a factor of 10. So let's impose the condition that the symbols for the delay spread be just 1/10 of the symbol. Okay, so let's impose the condition. Let's go back all the way. Let's impose the condition that the differences in the delay spread, which is the difference in these delays of arrival between the signals, is no more than 10% of the symbol time. Okay, that seems reasonable. So let's impose the condition that the delay spread is at most 10% of the symbol time. That's a pretty reasonable condition. So we had that the delay spread was 50 nanoseconds. That means that the symbols can be at most what can be 500 nanoseconds. Okay, so they cannot be short. They cannot be shorter than 500 nanoseconds. So let's make them 500 nanoseconds. So 1 over 500 nanoseconds is 2 megasymbols per second. So that means that at most we can send 2 megasymbols per second to stay in narrowband conditions, right? If we go faster than that, the pulses are going to be too short, and so we're going to violate this condition, and we're going to start to have wideband behaviors. Okay, so commercial systems today operate much faster than that, which means that corrective measures have to be used. We'll study this later in the course. Yes?
So you can have in-between cases, right? I mean, you're having frequency flats with ISI, right?
Yes. So the question is, you can have in between where the symbols are, say, compatible to the delay spread, for example, no? Yes, you can even have it. See, what happens is that you have to use correcting measures, exactly. So if you violate this condition, this 10% condition, and you start to have wideband behaviors, then you have to put an equalizer.
But what we want usually is using frequency flats. So it's more easy to correct the intersignal. It's easier to correct the ISI than to correct frequency selective, right? Because
Well, so the question is, if it's easier to correct ISI than frequency selective. Well, they're one and the same, right? So ISI is the time domain interpretation. And in the frequency domain, that corresponds to frequency selective. So the way you compensate for that is using equalizers that just correct these distortions. So we'll see some of that later in the course. But the point of this exercise is to show that indeed you need to do something about this, or otherwise you're constrained to using very low speeds. Exactly. So for example, on GSM phones, most of you guys have single phones, I think. So GSM phones use equalizers to correct for this problem. Okay. Okay, one final comment about polarization. Remember we talked about polarization, which is the plane of inclination of the fields. So how does multipath propagation affect polarization? This is pretty interesting. So let's imagine we send a signal that is vertically polarized. Okay, we send a signal with an antenna that has vertical polarization. At the receiver, after all these reflections in the environment, all these multipaths, how is the polarization going to be? Is it going to be still vertical or not? So the answer is that the channel completely randomizes the polarization, the multipath channel. So at the receiver, we're gonna find just about as much power in the vertical or in the horizontal directions. Okay. Not only that, we'll have about the same power in all directions, regardless of which was the original polarization. We'll take any directions that are perpendicular. We'll find the same power on both, and those signals are going to be pretty much uncorrelated. So what we receive from vertical polarization is going to be fed independently of what we get in the horizontal polarization. So this is a very useful property which can be exploited, and we will exploit it later. So at this point, that's all I want to say, that the multipath channel randomizes the polarization, and that orthogonal polarization directions exhibit about the same power and independent fading. Okay? So, summary, and you're out of here. So the summary refers to last week's part of the lecture, the second part, and today's lecture. So in these 3 hours, we've studied the small-scale channel behavior under the assumptions that the shadow fading is locally stationary. So we fixed path motion shadow fading and studied just the multipath fading over short scales. We've seen that it results in a linear time-varying impulse response that may or may not have a minor set component. We have all these components arriving with different angles and amplitudes. Because of motion, each one experiences a slightly different Doppler shift in frequency. So we send the tone at frequency fc, and we'll receive over each multipath component a tone at a different frequency within this interval, fc minus fd, fc plus fd, where fd is the Doppler spread given by the speed of motion divided by the speed of light times the frequency of the signal. We saw that the reciprocal of this Doppler spread gives us the coherence time, which is roughly the time over which the channel is going to stay constant. Because the multipaths have different lengths and so different delays, the signal is also spread in time, and the RMS delay spread characterizes the extent of this spread, and we have a precise expression for it. We saw that the delay spread allows us to classify, so Doppler allows us to classify channels into fast fading and slow fading, and delay spread allows us to classify channels into narrow band or wide band, and another way to say it, into frequency flat or frequency selective fading, if we see things in the frequency domain. And we saw the notion of coherence bandwidth. In the narrowband case, the fading amounts to scaling by a random process. In the wideband case, there is intersymbol interference distortion, which will need correcting measures. Whenever the number of multipath components is large, we have that the fading processes become approximately Gaussian, and so we can characterize them using the mean and the autocorrelation, and we study these quantities. The amplitude is Rayleigh whenever the components are Gaussian. And if there's an inosec component, then the Rayleigh becomes a Ricean. And sometimes we can have the Nakagami distribution that supersedes all these. For the narrowband case, we found particular insightful expressions using this Clark-Jakes uniform scattering model. And we saw that the multipath channel also randomizes the signal polarization. So just to conclude, we found 4 very important quantities, which I'd like you to keep in mind and think about. So we found delay spread, which relates to we found the nice spread in the time domain that relates to coherence bandwidth in the frequency domain, and these are essentially reciprocals. Okay, each one is 1 over the other one, roughly speaking. And then we found Doppler spread, and coherence time, which have a similar relationship. One is roughly the reciprocal of the other. These 4 quantities characterize the channel very precisely. Okay, so the nice spread tells us how much dispersion there is in time. So we send a very short pulse. How does the channel spread in time? Because of the fact that the different reflections have different lengths and so different delays. Its counterpart in the frequency domain is the coherence bandwidth, which tells us how far we have to go in frequency so that the channel is completely uncorrelated. So how far do frequencies have to be so the fading is essentially independent? So that's coherence bandwidth. The Doppler spread tells us if we send a signal of just one frequency, we're going to receive signals of different frequencies because of motion. Okay. And so how much spreading there is in frequency because of motion. And the coherence time tells us how long the channel stays constant before it changes. Okay? These are the 4 notions. And that's the essence of this lecture, is to understand these 4 quantities and how they relate to each other. And then you found expressions of how to compute some of them. Okay? So we'll have a second homework on the web. And I hope that going through the exercises is going to help you digest some of this stuff. All right? Thank you, guys. Good night.